Alright, so in this paper, in this video, I'm gonna be explaining this important paper, Diffusion Improves Graph Learning. This paper in NeurIPS 2019. Graph convolution is the core of most graph neural networks and usually approximated by message passing between direct one-hop neighbors. In this work, we remove the restriction of using only the direct neighbors by introducing a powerful yet spatially localized graph convolution. Graph diffusion convolution. Graph diffusion convolution leverages generalized graph diffusion, examples of which are the heat kernel and the personalized PageRank. It alleviates the problem of noisy and often arbitrarily defined edges in real graphs. So these are three contributions: proposing graph diffusion convolution, a more powerful and general yet spatially localized alternative to message passing that uses a sparsified generalized form of graph diffusion. Graph diffusion convolution is not limited to GNNs and can be combined with any graph-based model or algorithm. Analyzing the spectral properties of GDC in graph diffusion, we show how graph diffusion is expressed as an equivalent polynomial filter and analyze GDC's effect on the graph spectrum. So we define this generalized graph diffusion using this diffusion matrix. So S is the generalized graph diffusion. And T is the generalized transition matrix. Examples for transition matrix in an undirected graph including random walk transition matrix and a symmetric transition matrix. So special cases are personalized PageRank, heat kernel, and so on. So in graph diffusion, we have density defines edges, then we have sparsify edges here, then we have the new graph. Essentially, graph diffusion convolution exchanges the normal adjacency matrix with a sparsified version of the generalized graph diffusion matrix. This matrix defines a weighted and directed graph, and the model we aim to augment is applied to this graph instead. The general intuition behind GDC is that graph diffusion smooths out the neighborhood over the graph, acting as a kind of denoising filter similar to Gaussian filters on images. Most graph diffusions result in a dense matrix. This happens even if we do not sum to infinity. However, the values in S represent the influence between all pairs of nodes, which typically are highly localized. This is a major advantage over spectral models since the spectral domain does not provide any notion of locality. Spatial localization allows us to simply truncate small values of S. But GDC is based on assumption of homophily. For example, nearby nodes have the same labels. And then they talk about spectral analysis of GDC using spectral graph theory. And you can see it as a polynomial filter. Any graph diffusion can be seen as a polynomial filter. So we will extend the discussion to all parts of GDC and analyze how they transform the graph Laplacian's eigenvalues. GDC consists of 4 steps. First, calculate the transition matrix, Second, take the sum of equation 1, and then sparsify the resulting matrix by truncating small values. So we get S tilde. Then we calculate transition matrix using this S tilde. Calculating transition matrix only changes which Laplacian matrix we use for analyzing graph spectrum. We use L of sim or L of RW instead of L of UN. Adding self-loops to obtain T tilde does not preserve the eigenvectors, and its effect therefore cannot be calculated precisely. And then summation over this Tk. Summation does not affect the eigenvectors of the original matrix. So the eigenvalues of T are bounded by 1. We can use geometric series to derive a closed form expression of personalized page rank. For example, becomes like this. Sparsification changes both the eigenvalues and eigenvectors, which means that there is no direct correspondence between the eigenvalues S and S tilde. And we cannot analyze its effect analytically. However, we can use eigenvalue perturbation theory to derive an upper bound. So we have an upper bound. As a final step, we calculate transition matrix on resulting graph S tilde. This step does not just change which Laplacian we consider, since we have already switched to using the transition matrix in step 1. But there are limitations of spectral-based methods. While there are tight connections between graph diffusion and spectral-based models, graph diffusion convolution is actually spatial-based and therefore does not share their limitations. So GDC does not compute an expansive eigenvalue decomposition and preserves locality on the graph and is not limited to a single graph after training. For example, typically the same coefficient can be used across graphs. So they did on Quora, CiteSeer, PubMed, these popular node classification datasets. Co-author, computer science.